verify whether the cyclic data flow model is accurately designed. A quantitative analysis was subsequently performed on the cyclic data flow model implemented in this study. The test was conducted using actual equipment instead of a computer-based simulation, which differed from the actual environment. The test result showed that the performance of the cyclic data flow model using Raspberry Pi was adequate. SV frame follows the revised abstract syntax notation 1, specified by Bayes encoding rules, tag, length, pair encoding scheme. This figure illustrates the SV frame structure, which consists of a header, a payload, and a checksum. Currently, several studies have been conducted to evaluate the performance of a substation communication network through experiments and simulations. However, land simulation tools such as OPNet Modeler that are commonly used for studying the performance of a substation communication network are difficult to experiment within environments similar to actual sites. Therefore, in this study, Raspberry Pi, an inexpensive and open platform, was used to emulate real environments for conducting experiments. Iiccc 61A55 defines 7 different frame types and performance classes in a substation communication network. Specifically, type 4 raw data frames include cyclic and periodic sampling frames from an instrument transformer. These frames are time-driven data of a fixed length and are generated at the same predetermined time intervals and sizes. Cyclic and periodic data are modeled as shown in these equations. Scenario for transmitting the measured sampled values to the Iiccc61A59-2 Ethernet frame is shown in this figure. Wireshark is used to verify the Iiccc61A59-2 Ethernet frame in Raspberry Pi. The interlevel time of the SV frame generated cyclically was outputted as a graph. Python matplotlib was used to output the phase shift of the current and voltage as a graph for visual analysis. Iec61A50 SV frame generation diagram, which occurs cyclically, is shown in this figure. It can be observed that the SV frames of a fixed length are generated at a fixed interarrival time. This figure shows the result of analyzing SV frames captured by Wireshark. This figure shows the phase shift between the received current and voltages in the cyclic data flow model. Both current and voltages are generated with a phase shift of 120 degrees. In this study, a cyclic data flow model was implemented using Raspberry Pi in a substation communication network. A quantitative analysis was performed for the generated cyclic data flow. The traffic generated by Raspberry Pi in a laboratory model was confirmed through Wireshark for accuracy. In the graph, it is observed the SV frames are cyclic and are generated at a fixed interlevel time. The cyclic data flow model in this study can be useful in experiments on an actual substation communication network.
Hello, I'm Iiccc Kim, Department of Smarter Systems at Gwangwon University. I'll present 3D point cloud addressing structure using voxel index. Contents of this presentation is like from slide. Point clouds acquire the precise 3D information of the real world as a point set. Voxel is an extension of the pixel constituting the image into a 3D space, and the voxel size unit can be defined by the user. Our method is point cloud addressing using voxel indexing. The address points are structured into a voxel database and compare with the points estimated by 3D object detection to determine the user's location. The determined location information provides a visual positioning system and AR service. Unlike images, point clouds are generally sparse and are not placed at uniform intervals on a regular grid. When a point cloud is placed in a general grid, the number of points in the grid cell is generated unevenly. PointGNN use voxel downsampled point clouds for graphic configuration, and voxel used only to reduce the density of point clouds. VoxelNet represents points in 3D voxels, and some approaches keep the point clouds in 3D coordinates. Our method divides the point clouds of the indoor space into voxels of a certain size for VPS through voxel database matching after object detection in 3D space. The voxel database scans indoor space with a high-performance 3D sensor and calculates the overall size of the X, Y, and Z axis of the point clouds using the maximum and minimum values of the point cloud coordinates scanned. After dividing the X, Y, and Z axes of the calculated indoor space by the set voxel size, a number is assigned to generate a voxel address, and all points in the point cloud have the only voxel addresses. Figure A shows the internal appearance of the point cloud scanned with a 3D sensor. First, the scanned point clouds were aligned on the X, Y, and Z axes, and the voxel size unit is 02 meters. Figure B shows a 3D dollhouse view of the indoor space of the point cloud divided into voxels. Figure C shows a voxel grid. Our method can efficiently bring high location accuracy and direction estimation from 3D spatial object detection by structuring the point cloud in a well-known space into voxels. If there is not enough GPS, use a point cloud that can precisely obtain 3D data and address the voxel database. The voxel address in the 3D space may provide visual positioning use of fixed object indoors, and customized augmented reality content or mixed reality to the user.
Hello, this is Dongwook Lee, a presenter for the research group of Jinuk Jang and Dongwook Lee. I am here today to present my research topic, Substantiation for Location Image Classification Model, using Projective Template Matching and Convolutional Neural Network. This is the table of content that I am going to cover in the presentation. First is my group's research goal. Second is the referenced researches that we studied for application. And further are methodologies or approaches to our location image classification model construction, test results for each methodology, and at last, the research conclusion with future approach proposal. My group's research goal is to build an optimal model for efficient location image classification. Especially, we are aiming to classify the images for tourism attraction sites. And ultimately, my research group is looking forward to create a service model website by which the users can get the classification results of their input location images. This is the website prototype. So, if the user inputs the specific location image, the website tries to classify and gives the prediction result with useful information about the location. The research referenced three other researches. First is convolutional neural network. Second is the object detection model. And third is projective template matching technique. The first reference research, convolutional neural network, is a deep learning model for image analysis. This is optimized for recognition of objects and patterns in the image. This being so, it is being utilized in various fields such as medical care, architecture, and research. Based on the difference of inner detail such as layer formations, activation function types, and pooling size parameter, there exist different CNNs developed by several research groups. Examples of several CNNs are AlexNet, created by Alex Krzyzewski, Iiccc, which is formed by Oxford Research Group, and GoogleNet, which is created by Google. The second reference is object detection model. The algorithm beyond object detection model is based on convolutional neural network. However, unlike convolutional neural network analyzing the whole image as one class, object detection model tries to analyze all the sub-windows inside the image. Therefore, the end goal of object detection model is to detect and localize the objects inside the image. Projective template matching is a computer vision technique by which the algorithm searches for the specific template within the test image. One difference with the general template matching is that projective template matching has more degree of freedom by projective invariance feature. The searching of the template in the image is done by the pixel-wise calculations. The methodologies we tried for the model construction are the same as referenced researches. For convolutional neural network, we utilized Iiccc. For object detection, we used a YOLO version 5 model. And at last, for projective template matching, we referenced an essay from another research group which is to be introduced. Iiccc is a winner CNN model of ImageNet Large-Scale Visual Recognition Challenge 2014, which is a recognition challenge done by the company ImageNet. It is developed by a research group in Oxford University, and it is popular for its customizability. The image on the left is the original Iiccc layers, and the image on the right side is the Iiccc model constructed by our research group using TensorFlow on Python. For the work pipeline, we pulled the location images from Google and Naver search portals. After that, we went through manual pre-processing, filtering out the images with irrelevant objects and advertisements inside. Then we used TensorFlow to create the dataset and create the VGGNet for later prediction. The second methodology is YOLO version 5 model, which stands for You Only Look Once. There exist several object detection models, and YOLO v5 is mostly popular with its real-time predictability. The construction of the YOLO v5 model is referenced by Google Colab of the company RoboFlow. The pipeline for YOLO v5 is also similar with VGGNet at the beginning. After going through all the crawling and pre-processing, we annotated the images this time. Then, by training the YOLO v5 model, we were able to use it as further object detection model. As the decision tree, we tried to select the most accurately detect object inside the image and use it to classify the image as final result. The projective template matching is referenced by an essay, Robust Projective Template Matching, written by Chao Chang and Takuya Akashi. The algorithm is using genetic algorithm to create several candidate transformation matrices. And then for template comparison, the algorithm is using sum of absolute difference, which is calculating the sum of differences of all the pixels in the image window and the template. Since projective template matching is not using any deep neural network, we are not training any model for this approach. As we finish crawling and pre-processing, we select the region of interest for each location class as templates. Then we use robust template matching to find the template of each class in the test image. If the template exists, the image is classified to be the specific class of the template. As the test result, projective template matching showed the process time as above. The graph is showing the process time of searching one template in a test image. We can see that the time is proportionally increasing as the number of initial generation instances increases. Concerning all the parameter types and ranges, Chao Chang and Takuya Akashi proposed to create 2.5 million instances as initial generation. Conclusively, robust template matching is not suited to be used as a location image classification service model. For CNN and object detection models, each computation takes shorter than a second. Thus, we tested the accuracy of the model predictions as next step. Above graph represents the prediction results of 5 location classes. CNN predicts the location class with 46% accuracy with the standard deviation value of 0.43. YOLO v5 predicts the location image with 41% accuracy with standard deviation value of 0.34. And at last, as the combination of two approaches, we found that the accuracy of the model is increasing to 62%